Alright, so today we're doing angles in standard position in all 4 quadrants. So as I said, taking what we did on Friday and expanding it beyond the first quadrant. So let's say that we had angle theta at 40 degrees. That, of course, is in quadrant 1. Now, if I look at the angle in the second quadrant, that is 40 degrees up from the x-axis on the other side, what's the actual angle in standard position of that angle? Theta will be 180 minus 40. Okay, so theta is the angle always in standard position. Remember, it's measured from the positive x-axis. Counterclockwise. All right, now, if we measured 40 degrees this way, again, what would the angle in standard position, theta, be? Yep. Be 180 plus 40, which would be 220 degrees. And finally, if we go into quadrant 4 and we measure 40 degrees back from the positive x-axis, that angle in standard position, theta, would be what? 360 minus 40 degrees, or 320 degrees. All right, so each of these angles has only one value in standard position, right? Because as we talked about on Friday, in standard position means measured from the positive x-axis counterclockwise. But they all are connected to 40 degrees. Okay? So we call 40 degrees the reference angle. So here's another term that you need to become very familiar with. Okay? And the reference angle is always an acute angle. What do I mean by acute, other than good looking? Yep? Okay, so an acute angle is between 0 and 90 degrees. Okay? So the reference angle is always acute and is measured from the positive or negative x-axis. So all angles are measured from the x-axis. The angle in standard position and the reference angle. We never ever measure angles from the y-axis. Okay? Important to put that into your head, because I see people make that mistake all of the time. Now, there's different ways of denoting the reference angle. I learned this way, theta raw. So that means the raw part means related acute angle. So it's the angle connected to theta that is the acute angle. So that's the symbol that I tend to use for the reference angle. Your textbook tends to use the Greek letter alpha. So whatever you do, don't use theta, because theta is what we will always use for the angle in standard position. Okay, so theta is used for angle in standard position. And these are not the same thing unless what? Where is the angle in standard position and the reference angle the same? Let's go back to our 4 quadrants here. So here's quadrant 1, here's quadrant 2, here's quadrant 3, here's quadrant 4. Where is the reference angle and the angle of standard position the same? Yep. Quadrant 1. Because if the angle is in quadrant 1 in standard position, it will be acute, right? It has to be. Because all angles from 0 to 90 degrees occur in quadrant 1. It's not till you get into quadrant 2 that you go past 90 degrees. So the acute angle, the reference angle, will be the same as theta if you're in quadrant 1. So what we did on Friday, there's no difference between the reference angle and the angle in standard position. Once you get past quadrant 1, though, there is a difference. All right? All right, so let's just look at the quadrants. We'll do a quick review of quadrant 1. So we have our point P with our coordinates x, y, and r, and theta. And we know that tan theta is y over x, cos theta is x over r, and sine theta is y over r. And we got those from thinking about the right angle that we can create, right triangle we can create, where this of course is x and this is y. And that's how we came up with those three ratios. Now, whoops, lost T. Now when we move into quadrant 2, and we have our point P out here with our coordinates x, y. Now our angle of theta is going to be a much larger angle. And our reference angle, so I'm going to call it theta rho, just because that's what I'm used to calling it. Or you can put alpha in there. That's the terminology your textbook likes to use. Is that little angle that's measured from the x-axis up, that acute reference angle. Okay. Now, the ratios don't change. However, the values, the types of numbers they are, do change. Because in quadrant 2, what kind of values do x and y have in terms of positive and negative? What kind of value does x have? Negative. What kind of value does y have? Positive. So the overall value of the tan of y over x is going to be a positive number over a negative number. So it's going to be, sorry, I'm going to write this over here. So the tan of theta in quadrant 2 is going to have an overall negative value, because the x value is negative, which is why we don't like to think of it as a length anymore of a side of a triangle, because you can't really have a negative length of a triangle, right? But if you think of the value of the x coordinate in quadrant 2, it makes sense that it's a negative number, right? Sine is still positive y over, and R, of course, is always positive. Why? What's R represent again? Pardon me? No, I don't think about a triangle. What is R actually? What did I define R as on Friday? Sorry? The distance from? So from the origin to the point that you're looking at on the coordinate plane. So since R is a distance, by definition, R has to be positive. You can't have a negative distance. So R is always a positive value. Doesn't matter what quadrant you're in, because it's the length of this line segment, right? That's what R is, the length of that line segment. Length is positive, so R is positive. So in the sine then is a positive value over a positive value, so it's a positive value. And cosine, x of course is negative, R is always positive, so it has a negative value. Everybody okay with my short form for positive and negative? So in quadrant 2, can you see that if the reference angle was the same as theta in quadrant 1, would you agree that the sine of theta in quadrant 1 and the sine of theta in quadrant 2 would have to be equal in value? Let's say this was 40 degrees, and let's say this was 40 degrees. Do you see how they'd have the same y value? They'd be at the same height, right? And since sine is the y value over r, provided that the x value is the same, then the sine would be the same in quadrant 1 and quadrant 2. The x, the cosine, would be opposites of each other. We'll look at that more in a minute. All right, let's look at quadrant 3. So now, theta is measured all the way around. And again, this is my reference angle. This little angle in here. Okay? So what kind of values does y have in quadrant 3? Negative. And what kind of value does x have in quadrant 3? Negative. So what kind of value does tangent have in quadrant 3? If it's a negative number divided by a negative number, it would be positive. So it has a positive value. Okay, y is negative, x is always positive, so sine is going to be negative in quadrant 3. And x is negative and r is always positive, so that would also be negative. So this time, sine and cosine are negative and tangent is positive. Okay? Now let's move into quadrant 4. Yeah. So now we have our reference angle here, and theta in standard position is measured all the way around. So now theta's got a very large value. This, of course, is still our point with coordinates x, y, and this is still r. And the ratios are still found in the same way, y over x y over r, x over r. Now, what kind of value does y have in quadrant 4? Positive or negative? Negative. And x? Positive. So the overall value of tangent is negative. So y is negative, r is always positive, so sine is also negative. But x is positive and r is always positive, so cosine is positive. Okay, so that's the first thing, is to know where each ratio is positive and where it's negative. Now here's a little acronym that we use. So in quadrant 1, they're all positive. Okay? In quadrant 2, which one's positive? Just sine. And in quadrant 3, which one's positive? Tan. And in quadrant 4, it's cosine. So we call this the cast rule. That's how we remember it. All students take calculus. Something like that. However you want to remember it. Okay? So if you remember your cast rule, this is all are positive, sine is positive, tan is positive, cos is positive. Because other than in quadrant 1, there's only going to be one ratio that has a positive value in the other 3 quadrants. Okay, so that's just a way to help you to remember where they are. Now, before we go and apply this, let's just talk about coterminal angles. So coterminal angles are angles that share the same terminal arm. We talked about this very briefly on Friday. So for example, if I had my original terminal arm with an angle in standard position of 40 degrees, then I could measure it this way, 40 degrees. I could also measure it all the way around and back to 40 degrees. So what would that be? (360) plus 40, because we've gone, might be hard to see, so we've gone from here all the way around once, and then 40 more. Okay? So 400 degrees. Okay? We could go this way. Sorry. We could go this way. We could measure backwards. When we measure backwards, which is clockwise, then we call that a negative angle, so that would be negative 320 degrees. So you can have positive angles are counterclockwise, negative angles are clockwise. Just seems a little counterintuitive, I know, but that's the way it works. Whoops. We could go around and around and then come back and stop. So that'd be 720 plus 40, so 760 degrees. And I can go on. Those are all considered coterminal angles. So coterminal angles are any angle that share the same terminal arm. We can measure them in positive direction, we can measure them in negative direction. So because there are so many angles that have that terminal arm, you'll see in your book and in the questions that I give you that we restrict the angle theta to be between 0 and 360 degrees. If we don't put that restriction on, then there would be an infinite number of answers you could give us that would work. right? You can just keep going around and around and around and around, right, as many times as you want it. So to simplify it and to be precise, which we need to do in math, we will put those restrictions from 0 to 360 degrees on our questions so that you're only finding the first set of angles that work. All right. Any questions about coterminal angles? Okay, so let's see if we've got the 4 quadrants down first. So what quadrants do these angles in standard position lie, and give their reference angle? I.e. theta y. So I want you to tell me what quadrant you're in and then give me the reference angle. It's probably not a bad idea to draw yourself a picture. So tell me what quadrant those angles have their terminal arm. And then give me the reference angle. So the acute angle that we measured from the x-axis up to that terminal arm. All right, so as I suggested, you want to draw yourself a little picture. So if I go 65 degrees, and of course I'm in quadrant 1, and my reference angle is the same as my angle in standard position in quadrant 1. So they're the same. Now, this next one, I'm going 330 degrees. So I'm almost going a full circle. I'm going to stop a little bit short, but I'm definitely in quadrant 4. And since this is 330 degrees, how much more do I need to get back? Remembering that 360 degrees is a full circle, this would have to be 30 degrees. So my reference angle is 30 degrees. Okay. Now, I didn't show you this, but because I kind of thought you might know it, but maybe I should have. There are your 4 points of your 4 quadrants, right? 90, 180, 270, 360 gets you all the way around. So this one, when I'm going over to 200, I've gone past the x-axis a little bit more. So that's my 200 degrees. And my reference angle, well, how much past 180 have I gone? I've gone 20 degrees. So my reference angle now is 20 degrees. And I am, of course, in quadrant 3. Last one, I've gone 105 degrees. So I've just gone a little bit past 90 degrees. And the temptation is to do the reference angle in here, but it's not. Your reference angle is always measured from the x-axis, never from the y-axis. All right, so my reference angle in the last one is 75 degrees. And of course I'm in quadrant 2. Because I have to go another 75 degrees to get from 105 down to 180. Okay, so all reference angles are measured from the x-axis, never from the y-axis. That's important to remember. Otherwise, sometimes you'll use from the y-axis and that's not going to give you the right answer. Okay, any questions about that? Everybody get those? Awesome. All right. So now let's use this. So the point -3, 4 lies on the terminal arm of angle theta in standard position. So this is the same question we were doing on Friday. It's just that we're now going to be not in quadrant 1. So I want you to first determine the primary trig ratios. So sine, cosine, and tangent. And once we've done that, then we're going to find angle theta. All right. So in order to do the primary trig ratios, we need x and y, which we have, but we also need r. So how did we find r on Friday? If we knew x and y, how did we find r? R is equal to the square root of x squared plus y squared. Now, are we going to have any issues with this process if x or y is negative? Why not? So when you square it, becomes positive. So even though we have negative values for x and y, it's still going to allow us to find r. So this will be negative 3 squared plus 4 squared. So r is (9 plus 16) root 25. So r is 5. Okay, even though we know that if r equals root 25, it's plus or minus 5, we're discarding the negative 5 because r is a distance or a length. Okay, so now we have r. So now we can do our trig ratios. So tangent is y over x. So that's 4 over negative 3. Cosine is x over r, which is negative 3 over 5. And sine is y over r, which is 4 over 5. Okay, so all the same thing we were doing on Friday. Okay, the only difference is now some of our ratios are going to be negative because we have a negative x value. Okay, now before I started, I should have, my apologies, sketched a little diagram so we knew where we were. Right, so negative 3, 4. Means, of course, that we are in quadrant 2. Now, why is it important to do that? Well, because now when we go to find angle theta, we know that angle theta has to be somewhere between 90 and 180 degrees. If we don't get that, then we know we've done something wrong. All right. Now, to find angle theta on Friday, we did second function of any of the trig ratios, and I said it didn't matter which one you used. It matters now. So, to find angle theta, always use the positive trig ratio. Now, the reason for this, there are two angles that have two different angles in the whole coordinate plane that will have the same sine, the same cosine, and the same tangent value. All right? And when you start using negative ones in your calculator, it may give you one of them, but it might not be the one that you want. Okay? So your calculator will deal with the negative values, but it'll give you an answer that probably will end up confusing you. So instead of putting the negative values in, we're going to use the positive values, and this is going to give us the reference angle. And once we know the reference angle, then we can figure out what our angle is. Okay? So this will give you the reference angle. Okay, so keywords here. You want to use the positive key ratio, and you're going to get the reference angle. You're not going to get your angle. You're not going to get theta. You're going to get theta raw. All right? So I'm going to use sine because it's the positive value. And it's going to give me the reference angle. So theta raw is equal to the second function sine of 4 over 5. I put that in my calculator. And I get 53 degrees to the nearest degree. Now, I know that theta is not 53 degrees because it's in quadrant 2. That's why it's so important to draw yourself a diagram. Okay, because I always, on tests and quizzes, have people give me 53 as theta. But theta is in standard position. And 53 is the reference angle. So to figure out what angle theta is, what would we have to do? Yep.
180 minus 53.
So angle theta is 127 degrees. Right? And that makes sense because it should be between 90 and 180. So there's 2 steps to finding angle theta. First you find the reference angle using the positive trig ratio, and then you adjust for the quadrant that you're in. Make sense? Let's try one. So the point -3, -6 lies on the terminal arm of angle theta in standard position. So I want you, 1, to find the primary trig ratios. And 2, find the measure of angle theta. Okay, give that a shot. See how we do. All right, let's have a look, please. So I sketched my little diagram. -3, -6 has me down in quadrant 3. So theta is going to be between 180 and 270 degrees. So that's my sort of reference in my head. So first I need to find r. R is the square root of -3 squared plus -9 squared. So that's 9 plus 36. That's root 45, which simplifies down to 3 root 5. Okay, so make sure you're simplifying that radical. So tangent is y over x. So that's -6 over -3, which is +2. Remember from last year, tangent was the only ratio that could be greater than 1. Right? Because r, if you think of the triangle again, is your hypotenuse. So x over r and y over r, r will always be larger, so there'll always be a number less than 1. But tangent can be a number greater than 1. Sorry, yes? Oh, yeah, sorry. Thank you. How should be -6? I squared it correctly, I just wrote it down. I think I was thinking -9 squared. All right. So that's tan theta. Cos theta is x over r. So -3 over 3 root 5 becomes -1 over root 5. And sine theta, y over r, negative 6 over 3 root 5 is negative 2 over root 5. All right, so those are my primary trig ratios. Now I want to find the measure of angle theta. I'm going to find the reference angle first by going second function tan of the only one that's positive, which is tan. And that gives me 63 degrees to the nearest degree. So angle theta, I can see, is going to be 180 plus my reference angle, so 243 degrees. How many people were able to get all 4 of those pieces correct? Okay, any questions? All right. Okay, help me out. When does the bell ring? 12:47. Thank you. See, you guys always know. Yeah, he's right by the schedule too. That helps. Okay, so press till you knew it was right beside him. Oh well. Okay, let's look at a different kind of question. Find the measure of angle theta if cos theta equals negative 2 over 3 for theta between 0 and 360 degrees. This is what I was talking about earlier. I need to restrict theta between 0 and 360 degrees, otherwise there would be multiple, like infinite numbers of values I could give for theta. But I'm making theta a positive angle between 0 and 360 degrees. All right. So how do I define cos theta again? How do I find cos theta? It's a ratio of what? Yep. X over r. Okay? So if x over r is equal to negative 2 over 3, that means that x is either equal to negative 2 and r is equal to 3. Is there any other options? Is there any other way I can get a negative value for cosine? Because r, of course, has to be positive. So the only way I can get a negative value for cosine is if x is negative 2. Because r cannot be negative 3. Okay? All right. So where in the coordinate plane is x equal to negative 2? Well, right here. So I really have 2 options here. I have an angle here where r is 3, and I have an angle here where r is 3. So I have 2 values, possible values for theta. I could have this angle, or I could have that angle. So there's 2 possibilities. So there's 2 answers, 2 possible answers. All right. So this is a negative value, and I said we didn't want to put negative values into our calculator, but we need to figure out what theta is. So again, we're going to find theta raw first by doing second function of positive 2 over 3. Because the reason this works, if x is 2 or x is negative 2, if the y value is the same, and it would have to be for the same angle, then that angle and that angle would have to be the same. That's sort of what I was talking about earlier, and I said I'd come back to it. So if I can figure out the reference angle, then I can use that reference angle here and here to find those 2 possible values for theta. Yes?
Is it cosine negative or is it positive?
No, I'm doing positive 2 over 3 to get the reference angle. Okay? So that I can apply that reference angle to find the value of theta in quadrants 2 and 3. Okay? So put this into my calculator and I get 48 degrees. So then I know that that's my reference angle, which I can apply to the two different places. So theta is either 180 minus 48 degrees, which is 132 degrees, or theta is 180 plus 48 degrees, which is 228 degrees. And that's how I find the two possible values for theta. So I use the ratio, the cosine ratio, but I convert it to a positive number to find the reference angle. And once I know the reference angle, because I already figured out where I had to be, in which two quadrants my angle had to be in, I can use that reference angle to find the value, the two different values for theta. Tomorrow, we're going to still be working in 4 quadrants, and we're going to be looking at the some special angles, 30, 60, and 45, because they have some really cool properties that we use a lot. So I'm going to write the assignment down, and I'm going to stop this recording first.